Hello everyone, welcome to the last ROS tutorial. Today I'm going to talk about the lab practicals and explain the environment and what you can expect to do in the practicals. So far we learned some basics of ROS. Hopefully by now you understand how useful and powerful tool it is. Coding in it, it's very simple once you get to know the environment. Building up nodes includes adding several Python commands, and then you can have any block of code that you want in there. And ROS enables communication between different blocks of code through topics. And its application goes beyond robotics. Basically, you can think of it as in future, and any algorithm you want to develop that needs to rely on robust communications, you can do it in ROS, regardless of what it is for. And it's also really easy to connect your computer to hardwares using ROS. Any piece of hardware that you get, from camera to robots to anything, a Raspberry Pi board, Arduino board, any microprocessor, any type of sensor. And when you purchase this, it comes with a ROS package. And it's basically a bunch of nodes that you can use to communicate with that device. It's an API for the package. All you have to do is copy and paste that package, run it, then you will see some nodes that you can use to send command to that device. It makes communication with hardware very, very easy. And it's very useful, powerful software. So through the lab practicals and in this course, you will work with this ROS environment and think of it as an experience, gaining experience in some software development. All if you even don't really like ROS, go through the examples at this in this course. You get familiar with it. Install Ubuntu, install ROS, and then if you don't want it, delete it. You don't have to work with it. But for this course, please follow the instructions that I gave. Install Ubuntu using VirtualBox and go through the practicals. Today I'm going to introduce the practical simulated environment that you're going to work with. So far we had installed ROS in Ubuntu environment. If you download the first PDF file for practical, it gives you the link to the package that we're going to use in the practicals. First step is to download this package. I have already downloaded it. And similar to any new package, you want to put it inside your Catkin workspace in the source folder as we discussed. So I'm going to go to my Catkin workspace inside the source folder and put it there. If you're familiar with Git, you can easily clone it here as well, but I just copy paste it here. First thing is the name of the package is IVR Lab, so the folder should be IVR Lab. I renamed it to IVR Lab. 50% of the errors you run into is because you didn't name the package properly. It won't be installed. So it should be named IVR Lab. Then the next step is I'm gonna open up a new terminal to install this package. And as we said, we go to the Catkin workspace, install it using catkin make command. Catkin make will install all the packages that are in the source folder. And then when we install it, we need to source the setup file. Another 50% of the errors that you might run into is because after installation, you forget to source the setup bash file. Previously, I showed you how to do it, but if you put it in your bash file for the terminal, every time you open up the terminal, it will automatically source it for you. I've already done it in previous tutorials. So all I do is open a new terminal, close the previous one, done. The setup file is now sourced. This package has one file, Python file that you will code in it, and it also has a simulator running in Gazebo environment. You can run the simulator using a ROS launch file. ROS launch, name of the package IVR lab, name of the launch file is spawn.launch. Running this will open up the Gazebo simulator. It might run into some tiny errors. You can ignore these. If you see the robot in the simulation environment and it's working fine, the package is installed properly. So this is a Gazebo environment where there is a robot in it and a camera. Can I scroll to zoom out? If you're running a dual boot VirtualBox and you don't have enough memory allocated, Gazebo environment would be slow. It uses lots of memory and CPU. And because I'm running it in VirtualBox, it is going to be slow. That's why I recommended using clean Ubuntu installed. But no problem, even if you're running VirtualBox, we can work with this. I will explain later. But for now, I'll try to zoom out to show the whole robot to you. So I finally managed to zoom out. I had to close some background files running. So potentially, if you have a problem that the Gazebo is very slow, increase your memory for graphic card in VirtualBox. That should help. But we don't really not gonna use this environment. This is just to show how the robot moves. You can close this if it's too slow and keep programming. We're not gonna need this. I will show you later, but for now I'm gonna keep it open. And the robot that we have has 3 links and 3 joints. This yellow one, blue and green, and it can rotate at these joints. We have put a camera far from it to take videos and pictures of it. The goal of these practicals is to detect the joints of the robots in the first lab, position of them. Then in the second lab, we're going to use different methods to again measure the position of these joints. And in the third lab, we're going to use these to move the robot around. To take a closer look, I'm going to open up the terminal again. So this terminal is now running Gazebo. Keep it open, have another terminal. Even if you close the Gazebo environment, but this terminal is open, it's still running, and that's fine. Then you can speed up your Ubuntu if you have problems. You can close that, keep this terminal open. I'm going to take a look at the nodes. ROS node list. There are a bunch of nodes that are related to Gazebo. It connects that simulated robot to ROS. We're not going to use these nodes really right now. I'm also going to take a look at the list of topic. ROS topic list. There are several topics here that are mostly used to record the images. We're not going to work with these. There are 3 topics that are important. Robot joint 1 position, robot joint 2, robot joint 3. These are the topics that if you send commands to them, it will move the robot joints, the 3 joints. Let's send a command to one of these topics. ROS topic. If you want to send data, pub. Name of the topic, let's use robot joint 1. If you press tab, it will fill it out for you. Then the data type, if you don't know it, press tab, it will fill it for you. It's a float, just one number. Pressing tab again. Initially 0. The joints can change between half a pi to pi in radian. This is the degree that the joint will rotate with. I'm going to use half a pi. We'll send the command to the simulator, to the topic that the simulator uses. This joint moved by half a pi. You can do it with other joint as well. I'm going to send data to joint 2, joint 3. Let's move this by this time -4. It will move this joint. So this is the way you can move the robot. And we want to take images of it and then measure the position of these joints, the angles from images. I'm going to close this gazebo environment to make my systems faster. It is still running. If you go to the package for the practicals, there is one Python file that you will use throughout the labs. It's inside the source folder. It's called image processing py. Let's open it. This is a node that will get images from the camera in the simulator, and then you will code in here to process the images and measure joint angles. It's similar to the nodes that we developed before. Some new data are included, such as images, because we're going to deal with images as well, not just float, and a module called CV bridge. This will connect OpenCV to ROS. If you include this model, then you can use any OpenCV commands inside this code. I have created a class similarly like before for the node. Initializing inside the node, I'm initializing several subscribers and publishers. The node is called image processing. It has the ability to publish on one topic called image topic. It can publish an image on this topic. So if you process your images and you want to see it, it will be placed on image topic. There is another publisher called joint pose. This is when you calculate the joints, you can publish it on this topic to see what are the values for the joints that you have estimated. The rest of these, we're not going to be concerned about them. These are for the next practicals 2 or 3. And we also have this CV bridge, which connects OpenCV. And then the rest of the code, some parts of it are for the next labs, are commented out. What you care about is this callback function. As I said previously, everything we want to do can happen here. The way it's already programmed, it will get an image from the camera in the simulator and give it a name called CV image. From now, then, whatever you want to do, you can code it here to manipulate this CV image in using any OpenCV commands that you want. For instance, I have added a command to show the image from the camera. You can process it, use any algorithms that are discussed in the lab manual to process this image and get the values for the joint angles. And then you can publish it on an array here. When you calculate it, put the numbers in here, and then it will finally publish these two. It will publish the image. If you process the image and you want to see it, publish it here, and you publish the values for the joints that you estimated. Then you can compare the results, the values for the joints you estimated and the values that you given to it here using the publish topic command. If you want to do something more interesting, you can even send a command to move the robot joints on a sinusoidal trajectory between half a pi and pi, measure the joints using image processing, then plot and compare your results. Uh, to show how this node works, currently it's only set up to show the image from the camera. It only records the CV image from the camera in the simulator and shows it. So if I run it, it should show me the image. Using ROS run command, I can run this node. And the name for this is image processing. One thing I forgot to do, this is sometimes that gives you error. Whenever you bring a new Python command, you have to make it executable. So I'm going to do that now. I'm going to catkin workspace. Inside the source folder, there is my package IVR lab. Inside the source folder in it, there is my Python file for node. I have to make it executable. Done. Going back to the code, it's now executable, and it's going to use Python 3. Now, saving this, I'm going to run this node. ROS run, name of the package, then name of the file. See, it's showing me the image that it got from the camera that was in the simulator. This is the image that we're going to work with. You're going to use different algorithms on it to detect the joints and find its position. If you do it, for instance, in this case, I asked this joint to move to minus 0.5 radian, and this joint to move to 0.5 radian, this joint to move to minus 0.4 radian, this joint is kept 0. So if my image processing algorithm is successful, I should be able to get these joint variables and compare it with the commands that I gave it. This is what we're going to do in lab 1 and 2. And in lab 3, once you're more familiar with this environment, we're going to use these joint measurements to move the robot on a specific trajectory that we want. And one last thing is, if your computer is still slow and you have problem running all the simulators at the same time, one thing you can do is inside your Python code, write a command to save this image. For instance, using cv2imwrite. Then you will save this image in your catkin folder. Then close the simulator. Develop your image processing algorithms to measure the joints on that image offline. Once you're 100% sure it's successful, copy paste it in here and then compare your measurements with actual joints. This is how in practice usually we do it. We don't write the codes directly here because especially if you're working with a robot, you want to make sure that your code is working first. So we can save the data, write your algorithms. When you're 100% sure it's working, copy paste it back in this code for the node and test it. And finally, if you have any problems, concerns, post it on Piazza. Students, you can engage, answer each other questions, debug each other codes, and if you can't get any answer to your questions or you have more detailed questions, you can come to your lab sessions online and ask it from the tutors.